So we will talk about the construction of the ancient solution of the Ricci flow product. So let's move on.
Okay, so thanks for the organizer for getting me to Taiwan. Okay, it's a pleasant place to be. Today, I will talk about the construction of Asian solutions. So, Asian just means the solution exists to some time, you know. And often, later on, I will use tau equal to minus t. So basically, most of the time, I will talking about make sure the solution exists for tau go to positive infinity. So let's see. I basically divided the talk into three parts. First is some history about then I will talk about some rigidity result about in the last part I will talk about this is a joint work with Mackenzie Wang from McMaster University. So let's see. We care about Asian solution for a very simple reason. This is too long, so I just use. Because it come out of finite time singularity analysis, you always get Asian solution. So when we try to do it, we basically say, okay, whether we can find some Asian solution. Actually, you know, when we say Asian solution, another thing is we want to say it's not solitonic. Means it's not coming out from a rich soliton. So we want to say, okay, whether our intention, put it this way, is whether we can find a Asian solution which coming out from, you know, which is actually can be coming out from like a finite time singularity blow up model. But eventually, kind of, as we finished the construction, we find actually almost all of them is not this way. So to my knowledge, we don't know even a single one like that. Let me just give you a quick way to see it. So first thing is, if you have a type 1 singularity, there's one key thing. If you blow up, use a fixed base point. This is a shrinking GIS, Green Rich Soliton. This we know this is from you know, have a history. Then eventually this work out completely in the Anders-Mueller and Topping. Since it's solitonic, there's nothing to say. Certainly, this is the key. Then you look at type 2. Type 2, if you use blow up at the largest curvature, you get an eternal solution. So basically, all the construction you will see we did, all the example I will mention is not this type. Again, this is that. Because at a maximum curvature point, it exists. Then another thing is the example, most of the example we did, and also except one I will describe it, the underlying manifold is compact. But for compact manifold, there is a result by. If you blow up model is a compact manifold, then a result by Zhang says it must be a shrinker. So it's a kind of, before I even say anything, it's kind of disappointing to say is actually the good thing is singularity model is much restrictive than you worried about. Because the more Asian solution can be singularity model, then what you want to do, you screw up. Because you need to handle more enemies. Basically, that's the thing. I think that's the key thing. Actually, I want to emphasize. The left thing is technically is not that hard. We are doing ODE. Let's see. Give us such a. Yeah. So now let me give you some examples. So in 2D, there is so-called there's a Losner solution. The picture looks like the following. So let's say t equal to 0 is a perfect round point. So t equal to 1 it looks like this. So basically, t equal to -1, it looks like this. So in the middle, it's a very long S1 cross, nearly like that. In the end, you cap it, and the other cap it. So if you take a backwards limit, you can see this. If you take the backwards limit, you see this end. Use this as a base point. You see a cigar. And if you use some kind of the middle point to be, take the backward limit, the base point. So what you see is you see a perfect, S1 cross R. So that's basically the geometry. So certainly the base manifold is S2. That's a compact one. So maybe I just mixing the rigidity here is the work of Lopez. I think, definitely it's wrong. Hamilton, Sessom. Eventually in their work, this is the only one. In 2D. That's the only Asian solution. When I say Asian solution, I want to say non-solitonic. Okay. So their construction is by answers. You guess what this magic GT looks like. Eventually, in the expression, you have a few functions, only of time function. Then you say, okay, since this will satisfy rich flow, then AT/BT should satisfy some ODE. Then you get it.
Is this solution unique, or is this ancient solution unique?
That's the only one, up to scaling.
All ancient solution must look like this.
Huh? This is collapsed. I think this in 2D there's no non-collapsed. 3D you have. 2D you do not. Round S2 is not a solution to me. Okay, I said, or otherwise I will say some word again and again. Or whatever I say, modular this. If I'm wrong, then please tell me because I need to correct my knowledge. If modular this I'm right, so I'm right.
So is it a compact? Is this also compact?
This is a compact one.
That is a comparative solution.
No, I do not say this coming out from a finite time singularity model. So here is yeah. All I'm saying is under such situation.
But that is getting wrong.
What?
It's getting wrong in the end.
Yeah, in the getting it's actually this thing is rotational symmetric. Okay.
Can it be a cigar on one end and a sphere on the other end? Now, if you are joining the two cigars, right?
It's not a perfect system. What I'm saying is you take backwards asymptotic limit, you get a perfect cigar.
Yeah.
The solution itself is not.
Yeah, but is it possible the cigar on one side, sphere on the other side, on the other end?
No.
No.
Yeah. You may suspect something like that for high dimension, like I think it's 3 or 4 something, but not in here. Here the game is over. Right? Yes, it's a collapsed one. Yeah, yes. But the thing is, even the statement here is collapsed or not. That's only one. Yeah. So, okay. So, then such condition is also have a 3D. Again, this is done by done by answers. So you, I think the way is you look at this S3 in R4. So this guy have coordinates this way. Certainly, it's not an effective coordinates. You can say x4 is a function of x1, x2, x3, just like treat this as a unit 1. So okay, I should have put this in up index. Okay, so this I just copied from 孔胜利巴克斯孔胜利和倪磊的那个文章，下面我还要提到他们的文章，就是说你可以写出一个 answer 是这个样子，怎么了？啊？哦 ，sorry。Okay, good. So the point here is you guess the answers. Then eventually you see you have this is a function of t only. This is a function of t only. This is also a function of t only. And this is a function of t only. This is a function of t only. So you calculate, you get an ODE. Then if you can prove the solution exists, up to t equal to minus infinity, then you get an Asian solution. So it's not a homogeneous Asian solution, but the method is ODE. If it's in homogeneous homogeneous solution, certainly Ricci flow reduced to ODE. In some of work of Myers with others, they have like Asian solutions in them. Also, there's work about homogeneous Asian solution by Cao Xiaodong and who else? Okay, so I think I list somewhere. Yeah, so there's Buzzano and Laurette, and a few group of people construct the homogeneous Asian solution. So maybe I should write down. So then it's also an ODE method. So next thing, let's talk about Paraman's Asian solution on SN. So let's see. The way you do it is you want to construct a sequence of solutions. Then you get another sequence of solution. Then you take a limit. you get an Asian solution. So basically, that's the way of construction. So this is a method of Y compactness. Let me try to describe what is that. So you can have t equal to 0. You can have this one. Let's say Sn minus 1, radius 1, cross minus L. Maybe use I. Then you cap it. Use a standard way to cap it so that this have a non-negative curvature operator. You just cap it. So the middle is from minus I to the I. And you can make it a rotational symmetry. If you have such a solution, because the curvature operator is non-negative and positive somewhere, so you know it flows. And eventually flow to this one, and the perfect round. Eventually, like a little bit like this, or almost round, then perfect round. This is the work of bomb working. Okay, so this will give us solutions. So it's from 0 to some Ti. So okay, then what you do is you want to find this time called Ti, such that at this time the maximum sectional curvature at this time and the minimal sectional curvature at this time is exactly, let's say, 1 plus epsilon. Fix some small epsilon. Just like you see the just the epsilon away from perfect. If this ratio is 1, then you get a perfect Sn. So you just like an epsilon away. Epsilon is very small. Epsilon away from the round. So then you say, okay, this is my new times 0. Then you blow up this so that equal to, let's say, volume equal to just omega n. Standardly, it's n omega n, I guess. It's just a standard unit sphere's volume. So basically, you get almost a unit sphere. So I need to draw a kind of perfect round. Suddenly, I put some badness here, something like that, just like that. So this is my new times t equal to 0. So if it's a kind of this one is very tiny, then you blow up this large, then also you move this time to 0. So basically, you get this thing will be very fat and extremely longer, this one. And this time will be minus Ti tilde. So this will be a number. You can basically say, you say this number. You need to argue it's go to minus infinity. This is our Gi tilde. This is our Gi tilde. This is the approximate Asian solution because it's almost ancient. But it's not. Then you just say, okay, you pick any point here. So this sequence with base time 0 we are convergent. Because the existence time getting longer and longer, you can prove this will be a limit will be Asian solution. Because this this part is like a not perfect round, so you can prove this limit still have this condition. So this guy will not be round. So that's basically roughly how Penman's Asian solution is constructed. Again, I want to say is this manifold is compact. So the other way, this method is used again by Takahashi, and he constructed an Asian solution on this one. It's a 4-dimensional. And also, it's non-compact. So that's the example I note, which is, homogeneous, let's say. I should say also homogeneous, I didn't pay close enough attention, just like this non-homogeneous also. This one. The way he did it is, this guy have a Schwarzschild instant metric on it. Then also, if you look at the Ricci curvature's linearization, it have an unstable direction. Let's use H. So if you think about the metric space, all the metric space, you have this is GE. Now you choose parameter. So if you have parameter, now you have this initial. You have this initial metric. So basically say this is the tangential direction of H. So let me see, I have a color chalk. So if you go anywhere out, so this is G delta 0. Then you have a Ricci flow. Just initial condition. So certainly T, in this way, what you get is you get a solution exists on such time. The thing is, we still need, basically it's kind of this tell you how do you get this. Replace I, parameter I here by parameter delta. The thing is, how do you get this one? So you need a solution like exists backwards, closer and closer to negative infinity. So what they did is you use a shift of time. I think it's log delta. Yes, it's log delta. So basically, your new solution I think that's the one. Yes. So shift. So now when this initial time, when this whole thing equal to 0, means this t equal to this. Because delta is small, so this is the number go to negative infinity. So then you take compactness of this family of solution. So in a picture, probably I can draw it like this. So you have another solution like this. You have another solution go out like this. Eventually, in the limit, you get a solution go out like this. It's kind of this. You can get an Asian solution coming out from this unstable direction. That's the one. So. Yeah, so. So this is also compactness approach. Finally, let's say an example due to Simon Brenner and Kapolis. So it's also on a compact. So it comes from this. It's a kind of similar to this Kuma construction of K3 surface, but the gluing was different. So torus T4, you can have this reflection action Z2. Then this action have 16 orbifold points. What you do is, okay, draw a picture which is so 16 points divided by two groups. One group is 8 points. The other group is another 8 points. So you glue each of them. This is like orbifold point. You glue each of them by a so-called Iguchi-Hansen matrix. So it's a kind of draw a long picture to say things. It's kind of Iguchi-Hansen matrix. So you smooth this out. Iguchi-Hansen matrix is asymptotic Euclidean. So it's a kind of you choose here is another parameter. I don't know. We say this is a parameter J. Just how far you get into near your corner point. Here is where you scale this part very close to Euclidean part. Scale this as small to fitting this. Then since after scaling, this whole thing becomes very tiny. Then you just fitting this here. That's a kind of gluing stuff. So the key thing I want to say is you can have a parameter J here, depends on where you glue it. So it's unlike the construction, use gluing to construction, the KE matrix. They glue, half of them use one orientation, you glue other half use other orientation. So then you get something. So what they did is you get one metric. Let's just use AL. This time T. This time let me make things clear. This solution exists This 0 is not important, can change that. This is almost Asian, almost a rich flow. But it's already ancient. Let me explain. Basically, it says you you divided this time interval into tj plus 1, and tj plus 2. So each time you choose tj, you let this flow run enough time so that you reach next tj. So it's you fitting all these different gluing together. So eventually you just get it's not a solution of rich flow unlike over there, but it's ancient. So I want to say this method is PDE method is. So then they run a singular perturbation argument. So then this solution you get a GT. Let's use infinity to denote it. So this is a rich flow solution. There's lots of weight function used to do the singular perturbation. To me, the fancy thing is the manifold itself is compact. But when you do singular perturbation, because you're including time, this is non-compact. That's to me, the very fancy part of this this construction. So that's a PD argument. Okay, let's except I lightly touched this homogeneous Asian solution. This is basically the examples I'm aware of. Okay. Yeah.
Last example, as t goes to 0, does it approach the initial thing? Is that right?
T go to 0, it approach to this flat conic one.
Yes.
Yes.
Right.
Yes.
Initial thing to start.
All is popped. All this gluing Gucci Hansen is popped out. Yeah. Yeah. Okay. So, any other questions? Let me mention some legitimate result. We already said one about 2D. So here is another one. Just any closed type 1 carbon non-collapsed Asian solution with curvature operator bigger than 0 is a quotient of round sphere. Now I understand what terminal says. Basically, you try to emphasize if carbon non-collapsed, there's no such thing actually. Yeah, this is Leibniz results. Okay, so that's another one. So this is for all the dimension. It has two parts. In 3D, it's if the Ricci curvature is pinched, then it's run as 3. So basically, it's kind of, if the curvature is pinched, the Pelleman's solution cannot be a candidate here. It's ruled out. So in higher dimension, the curvature pinching condition replaced by the following. Then it's also run as n. So we know that there's conjectures about it, like under what circumstance the solitons must be like blind, must be this like a FIK. Here is a question about a kind of rigidity of the Asian solution. I need to add a compact. I need to add a non-collapsing. Also, I add 3D. So basically, it's kind of, you want to say, the Pelleman's solution is very special. Because of the Asian solution, this is actually listed in a book by Ben Chaw, Laney, Hammond, and Rich Flow. This solution have curvature operator, because it's 3D, have curvature operator bigger than 0 by the result of Chen Binglong. So it's kind of, you may try to raise questions in higher dimension, but in that case, you definitely need to add at least one condition, curvature operator is positive. So this is, this is kind of also try to, at least try to tell you in 3D, because a singularity model satisfy all these conditions, except type 1, we don't care. So basically, to try to say in 3D, if you have something, no, it's also not right. So because this is compact, it cannot be as a singularity model. Yeah. So, okay, so. Maybe I have less than 5 minutes, right? I think. Maybe I just stop here. In the afternoon, I will say what we did. Yeah. Thanks.
So parent engine doesn't have an explicit form, yes?
No.
So
This,
Yeah, I know this is a certain. I mean, why I think in this statement, it has already implied that S3 over gamma is impossible.
the thing here is, if you say, let's say, if you have a Z2 action, probably it's okay, right? You can have a Z2 action because you can reflect the two ends. Otherwise, except you get a brand new example, the two ends.
Right. I'm just asking how we rule the Z2 action.
No, Z2 action should, maybe. So let's. Yeah, so it's a kind of you add enough condition to rule out this Fadefi example to say, just like say, basically you need to construct a, Asian solution other than these two groups, Fadifs and Paraments, whether you can get something. So it's kind of, yeah.
So, if a solution is not ancient, what are the possibilities when you move time backward?
Oh, you just cannot move.
So what will happen?
Nothing happened because there's nothing satisfy the equation. Let's say you already have it's like a heat equation. You cannot go backwards.
Yeah, but what happens in the moment when you cannot go further back?
Oh, let's say you start with a C2 initial data. You solve solution, you get a forward in time. You say, can I push this back? It's impossible because of the analyticity. It's a kind of, you say, what happens before Big Bang? The point is, a Big Bang is singular, so then you cannot say whatever before that, why you go through Big Bang is a continuity. So, right, why does it have any connection?
The question is exactly on what happens in reality.
Backwards?
Yeah.
There's no sense of usually singularity except you cannot go back because you do not have blow up the curvature. Your solution is in some sense like a complete, means you have all the bounded data. You say things go back except it's only C2.
Like you cannot go back to yesterday.
Yeah. Yeah, that's a basic heat equation.
The final equation, if you go backward, it's not where pulse.
Yeah.
It's ear pulse problem. You go
Yes.
backward. So, any more questions? Do you have less than 12 minutes?